All right, so last time we finished talking about, here, let me just turn down my volume. Something binged. There. Tournament selection. And tournament selection is easy to implement, simple to implement, easy to understand. It's got a lot of control over the selection pressure. It's fantastic. Now, an alternative, an alternative broad category is called fitness proportional selection, where the general idea here is each chromosome's fitness value dictates its probability of being selected. Where with tournament, it was a little different. With tournament, you randomly pick a subset, then you take the best one. Where this one explicitly gives each chromosome a probability of being selected based on its fitness, or its proportional fitness relative to the rest of the population. So in general, the probability of picking an individual is its fitness divided by the sum of the fitness of all members of the population. So if you go through each chromosome, I think I have an example down here that we'll work through. That's the idea, is you just add up the fitness of all the chromosomes in the population. You take each individual and you divide it by the total, and you'll get like a percentage, right? And that is its probability of being selected. The benefit here is selecting highly fit individuals. It gives us, like this, we don't have as much control over the selection pressure as we do with tournament selection, but it's like a dynamic strategy where if something's really, really, really good, it's going to have a really good chance of being selected. Where with tournament selection, you might get unlucky with every subset you pick, and you might never ever pick the best one. Same thing could happen here, but just with how it's done, you'll kind of see. But there are issues with this selection, and when I'm pointing out these issues, I'm not saying that these are detrimental issues that because of these issues you should therefore not use this. No, 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 no. These are just things to keep in the back of your head. It does get stuck at local maximum because what will happen is as the population converges, everyone's fitness becomes more and more similar, meaning that you effectively have a uniform selection. Which, okay, not necessarily bad, but kind of bad. And it's important to ensure that our population stays diverse. Now, you can't use fitness as a direct measurement of diversity. You can't. What happened? Oh. Yeah, you can't use fitness as a direct measurement of diversity. You can't. Just because two things have similar fitness values doesn't mean that they are similar in what they mean in the phenotype space. Or genotype space, even. And just because they have very different fitness values doesn't mean that they are very different in the phenotype space either. It doesn't necessarily mean that. However, it's a pretty damn good proxy. So when everything has a similar fitness, you know, there's a good chance, at least it's intuitive to think that they start to look very similar. So you don't really have much diversity in the population, which is a bad thing. We don't like that. Further, yeah, okay, like I already said, as it converges, this becomes more similar to uniform selection, and learning will stagnate. And it'll become dependent on whatever mechanism you have within your evolutionary algorithm that adds that exploration, that can add that diversity to the population. So, you know, commonly with the examples we've used, that would have been like the mutations, which are not necessarily always explorative, but, you know, it is in the examples that we've seen so far. Modifications of the strategy include some ways to address these issues. Like something is like windowing. Windowing is a subtraction. So what you do is you subtract the lowest fitness from everything. I think I've got that in the example, and you'll kind of see how it affects how the fitness is. Yeah, so here we go. Yeah, here we go. Look. So let's say I have 3 chromosomes. This is obviously a very small example, where the fitnesses of these chromosomes are 1, 4, and 5. And here, let's assume this is a maximization problem, where a bigger fitness is better. So if you take the fitness as a proportion of the total fitness, it's going to be, so the total fitness of the population is 10. Why? 5 plus 4 plus 1 is 10. So 1 divided by 10 is 0.1, 0.4, 0.5. So here, every time for selection, I would have a 50% chance to select chromosome C, 40% to select B, and 10% for A. Now, how do we do this? Random number generators, right? You just pick a random float, and then you kind of like, you rank it. If you roll let's say, for example, if you roll a 0.3, well, 0.3 is less than 5, so 0.5, so you select C. If you roll a 5.5, well, that's between here and the sum of these two, 0.9, so you'd select this one. If you roll a 0.96, well, it would be this one. Hopefully that's obvious. If not, just think about how, here. Let me make it more obvious. Can you see that reasonably well back there? Probably not. I'm gonna grab a different marker and go over there. Wow, what a terrible, terrible thing. So here, we'll have, this sums up to 1.0. And so here we have, this would be chromosome C, B, 0.4, and here we have a chromosome A. Right? Does that make sense so far? How, right? But like if you take this, what does this add up to? 0.9, right? And if we had more chromosomes, I would keep doing that all the way up, where you sum the total all the way. So if I'm rolling a number, and I get a number here, like pick a number between 0 and 1. Literally any number. 0.72, 0.72, 0.72. Well, that's less than point, so we're here. Right? So where do we go? We pick B. Pick another number. 0.3. That's about here. Oh, we'd pick C. Pick another number. 0.92? That would be up here. Oh, we picked A. Another number. 0.33. That's around here. Right? You see, that's how it would work, right? This should not be scaring you, but just maybe to put it as a picture, it should be a little clearer. So that's how we would actually do the selection here. Sometimes you call this roulette wheel. Well, actually, a specific implementation of this is roulette wheel. Imagine you have like a roulette wheel, except the side, raise your hand if you don't know what roulette is. All right, fine. Let's just, that game in the casino? Here, you know what, here. Oh my goodness. There. Right, like that, right? Each chromosome would be on there, except unlike this, where here every single number has its own, like it's an even space. This would be uniform selection. You are equally likely to pick any of these numbers, okay? But with what we would do is we would make the ones that have a bigger fitness have a bigger spot. And the ones with smaller fitness would get smushed. That's the idea. That's the intuition. You can kind of like start to cheese this if you want you can add some baseline value. Perfect, thank you. You could add some baseline value. Here I added a 10. The fact that this is 10 and this is 10 is not necessarily meaningful. We added a 10 and then you redo it and suddenly you kind of like, those that are better don't dominate as much by adding like this like base number. Do you see? And windowing is an example of, well, what you do is you can subtract the minimum out. So you subtract the 1 from everything, and then you redo the calculation, and then that's how you can kind of like change. Basically, by adding or subtracting a value to the fitnesses, you could get a little bit more control over how much you want good ones to dominate or how much you want good ones to not dominate as much. So there is some control with that. But to me personally, I find this strategy as a mechanism of controlling selection pressure a little less intuitive than tournament selections K. But if you like this, by all means, more power to you. Rank-based selection. Okay, what is this? Okay, an alternative is to take the same idea but rank the candidate solutions, then have the probability of being selected relative to the rank. Yeah. So here's their fitness, but what you do is you rank them instead. Well, the ranking ends up being the same as windowing in this situation, but I don't know if that's always true. Now, of course, it won't always be true. But you rank them, and then their proportion of being selected is based on their rank, not exactly their fitness. But it is their fitness like indirectly. So roulette wheel. Here's the idea. This isn't a roulette wheel now. This is a like spin the wheel game, right? You spin and it goes, you know, like that. And then wherever it lands, that's what you pick. The bigger piece of the pie here, A has the biggest piece of the pie because it has the biggest fitness, and as it based on their proportion, each slice of the pie is proportional to its fitness value. That's the visualization there. But I spun the wheel and we land on yellow. Yellow is D. We selected D. Great. Questions about this, or are we happy? Cool. So this part, admittedly, I'm not even 100% sure why. Someone explained it to me once, and I didn't quite get it. But for some reason, for selection, oh, something didn't render here correctly. It looks like I missed a backtick. Someone can fix that if they want. The backtick would be between the colon before the L, by the way. Do I explain why? Although it's possible, finish before selection, only for small. Yeah. Long story short, instead of spinning the wheel multiple times, what you do is you can have, instead of spinning the wheel lambda times, you have lambda arms, and you spin the wheel once. I don't know why it's better, but people claim it's better. I was never convinced, but you'll notice if you go through the literature in the textbooks, you'll see this talked about. And if you find out why, let me know, because I could never really make sense of why it would really matter. So here's an example of it with 2 arms. There you go, right? You spin it and yeah. Any questions? Are you actually fixing the PR? Are you going to try to do it? Cool. It's under topic selection. Okay. Next, survivor selection. So now we're in the situation where we're talking about a steady state algorithm. One of the not a generational. The previous selections we just talked about are typically used in generational and for steady state for selecting who gets picked. To get like who's eligible for crossover and mutation and going on to the next generation if it's generational, but like who gets picked. Now you could do something similar you could do tournament selection to decide who gets replaced too. But of course when you're doing tournament selection, you want to base it on like fitness. So do you do it, I guess if you were to do that, you'd want to pick like the one with like the worst fitness, I guess. But then you're doing a selection strategy, a survivor strategy, or a die-off strategy, basing it on those with the worst fitness should die off. Which isn't a bad idea, that makes sense. But that's not the only way to go about doing this. Nor is it necessarily a particularly good way of doing it. Not to say the other ways are better, it's just, it always depends. So with a steady state algorithm, we need survivor selection. Remember, survivor selection is, remember, with a steady state, we've got a population, and it's one population. We select two, maybe they cross over, and I got to put them back in the same population. But if I have, what was it, mu things in here, and I selected two, now I have mu plus 2, but I need to pick 2 to replace, to put them back. How do I do that? This is what we're talking about right now. Do I take the 2 that have existed the longest in the population? Do I take the 2 that have the worst fitness? Do I take the 2 that have the least diversity? Do I just replace the 2 that I just selected? This is the question. So any rule could work. Random. Randomly select lambda. Remember, lambda is the number of things I've selected. Randomly select lambda to replace. Okay, yeah, a uniform strategy. That could work. There's nothing wrong with that. Age-based. Replace the lambda oldest individuals. So this would require a little bit of extra bookkeeping where the population, each chromosome, we would need to know how old each chromosome is. Like how many mating events it's existed for example. So this particular strategy, it ignores fitness, but it might kill off the best individuals, which isn't necessarily a bad thing for the search as a whole, but that could happen. Fitness-based, replace the lambda worst individuals based on their fitness value. And it'll kill off the worst candidate solutions, but this might destroy diversity. Because remember, although fitness is not a measurement of diversity, sometimes it's a pretty damn good proxy for it. 2, 3, 4, 5, 6, 7. Perfect. And so this could cause the population to converge too quickly. And diversity-based, this is a really interesting one. And I like this one, but there's a big problem with this one. Replace lambda candidate solutions that are the most similar. The idea is replace those that add little diversity to the population. But there's a big problem with this one. Anyone want to take a wild guess what the big problem with this one is? It might. That's not what I was thinking, but that's a point that could be the case. Because it is possible to have things with the same fitness values that are very different from one another. This is where we got to be, it's not, it can be used as a proxy, but yes. But when we're talking strictly about diversity, to me, the big problem is, how the hell do you measure diversity? How do you measure how diverse a candidate solution is from every other member of the population? And there are ways to do it, but now we need a whole other mechanism of evaluating each chromosome. How diverse is it relative to the rest of the population? It's almost like a whole other fitness metric, really, where the fitness is how different it is. And similarity-based. Replace the lambda candidate solutions with the most similar fitness to the offspring. So this kind of tries to cheese what, if it's got a similar fitness value, maybe it's not very diverse. So, that's maybe a quick and dirty, easy way as a proxy for diversity. If it has a similar fitness value, replace that. Although it might not be, yeah. But then again, with this strategy, we don't need to measure diversity, which is a whole other headache to begin with. So it's always give it a try, see what happens, see what works. You might notice at this stage, we're like more than halfway through the semester now, right? I have no idea what week we're into now. If you are the type of person that doesn't like changing your code once it's written, and I don't mean like tuning parameters, I mean like going and refactoring and changing out chunks of your code, you're probably not the type of person to be good at evolutionary computation. You're going to have to be trying a bunch of different things. You can't just pick and set, I picked this selection, this mutation, this crossover, this hit run, tune it and be like, okay, I'm done. You've barely started. You need to change out those things and try those things. See what works, see what doesn't work. Yeah. Yeah, okay, so similar diversity and easy to implement with an assumption. Those with similar fitness may be similar in the genotype space. So like we were talking about the the diversity. Now, elitism. We've talked about this before, but not directly. Actually, before I talk about this, do we have any questions about any of those ideas so far? Remember, like everything so far, everything is just an abstract idea. How you implement it is entirely up to you. And to me, that's what makes this stuff fun. You have a loose recipe for how to do it, and then you get to be as creative as you want, and that's fun. Okay, elitism. So, every once in a while, someone will come up with an idea. Often, they're very simple ideas, which is nice. Someone will come up with an idea that becomes like integral to a successful evolutionary algorithm. Elitism is one of those ideas that it's obvious. To me, it's obvious, and it's commonly used in evolutionary algorithms because it works so well, and it's so easy to implement. Regardless of using a generational or steady state algorithm, elitism is commonly used. The idea is always, 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 always ensure the top X chromosomes from your population will make it to the next generation. This eliminates the ability for your best chromosome to die off. If you ever see your learning curve look like this, where the best gets worse, I don't know if you can see that well, this marker sucks. If you ever see it go down, I know you don't have elitism implemented. It should never go down. That's elitism. That's the idea. It works well. It's easy to implement. I always recommend doing it. And it should be obvious why it's handy. But you got to be careful. Always keep the number that are like elited to the next generation. Always keep that number small. I always use like 1. I think I used 2 once when I had population sizes that were like astronomically large. Always keep it very small. Because as soon as you make it too big, things are going to converge way too quickly. And you can experiment this. If you don't believe me, try it. And you will convince yourself that as you crank X up, you're going to converge way too quick and you're probably not going to find the best solutions that you could. Any questions about elitism? Raise your hand if you used elitism in assignment 1. Good. It's a good idea. All right. Oops. Diversity. Diversity is how much a member of the population differ from like the rest of the population. And it's a very important thing within the population. There are actually some of like the more interesting, noteworthy, some of the most interesting and noteworthy changes in the last decade in the world of evolutionary computation are all based on diversity. It's been like dubbed novelty, but it's just diversity, where novelty is something new and different in your population. So we really want diversity. It's that exploration and exploitation thing. In order for your evolutionary algorithm to work, you need both, and they need to be in a big balance. It's almost like, it's one of those things that when you look back, it's obvious, but at the time, 10 years ago, it wasn't that obvious. But now you look back and you're like, how dumb were we? Obviously, we need a really good way of preserving diversity in evolutionary algorithms. So in the last 10 years, people have started like shoving mechanisms and ways to make diversity exist within the population to ultimately help your final results, which is really good. Some of the stuff in novelty search, they throw fitness out the window and they just do basically everything on novelty. I mean, they're working with special problems where that's workable, but it's really interesting nonetheless. So yeah, diversity is important in the population. It balances exploration and exploitation. It helps prevent premature convergence. We don't want that. When I say premature convergence, if you don't remember what I mean, it's when your this versus this, right? This might get there faster, but it's stuck. This would be if I saw 2 plots, if you and you worked on this problem, and one of you had a line that looked like this, and one of you had a line that looked like this, I'd be like, you converged way too quickly. Because clearly you could keep going. You'll never know if you've got premature convergence if you don't keep running things. Yeah, okay. As with anything in evolutionary computation, there's no rules on what should be done, but below are some high-level ideas. Now, some of these will explicitly add diversity. Some of these will be a mechanism that tries to implicitly add diversity. Some can be ways to actually measure diversity. There's a lot of different things that you could do. I'm only going to show you a few ideas. All right, below are some high-level ideas, but in no way exhaustive. Explicitly add diversity measured to the fitness calculation. That's easy. Now, we haven't talked about multi-objective optimization yet. We haven't talked about that yet. We will soon. But if I've got my fitness value, and I have a mechanism to measure diversity, where I can like crunch it down to a number, then, well, maybe I could just kind of like add those two numbers together. If a bigger fitness value is good and a better diversity is good, you add them together, it's a bigger number that's more fit than one with less diversity. So that's an idea. Explicitly measure diversity and add it to the fitness calculation. The downside of this is now we have a whole, like, what is the computational complexity of measuring the diversity of a candidate solution of the whole population? How much time is that going to take? You're going to do that for each generation? My goodness. But maybe it's worth it. Or maybe it's really not that much work, right? If it's another linear time operation, yeah, you might double the run time. I don't know, but maybe it's worth it. Here's one. Only have similar individuals ever compete with one another. Now, this could be done through selection strategies. So this would be a little bit more indirect. Now, here's one. This is an interesting idea where, do I not have? Okay, I do. The island model. This one's really popular. What you do is you take your population and you say, okay, if I have a population of 500, what I'll do, no, actually I'll use 300 because the example below I have 300. I'll just show you the picture. If I have a population of 300, what I do is I actually break that population of 300 down into 3 separate populations. And selection and mutation and crossover happen independently from one another. So these populations start to evolve in isolation. How many times have you hit run on your evolutionary algorithm and then hit run again and get wildly different results? On every time you've ever used it, right? Obviously, that's what's going to happen. So if you run these things in isolation, they're going to get very different from one another, likely. So you have them run in complete isolation. But every once in a while, you allow migrations to happen. Think of these as like islands with birds that can fly between them or something, right? So every once in a while, maybe every 1,000 generations, every million generations, I don't know, you allow 1, 2, 5 members of the population to go here and 5 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 there, right? You allow that to happen. Every 1,000 generations or so, whenever you allow a migration, you really add, like you are really injecting some diversity into this population, which is pretty neat. So this doesn't directly add diversity, but now we've added like a mechanism that implicitly will add diversity, which is pretty neat. And this is actually a relatively common strategy that you'll see in a lot of evolutionary algorithms. And there are some interesting reasons why this is popular too. Raise your hand if you have a threaded processor, multiple cores. Yeah, there you go. What people will do is they'll be like, well, this is easy. How many cores do I have? 8? Awesome. Let's have 8 islands. And you run them in parallel and you're all good to go. Great, right? Cool. There is some issues there where you could be wasting a lot of time. So, by the way, In practice, that's actually not a good idea. Because what will happen is, if you have 8 cores, in one core, every time you hit run on these evolutionary algorithms, based on a lot of different things, it has a different runtime, right? So the amount of time it takes to do 1,000 generations is going to differ per island. It always will. So if I have 3, 4, if this is like time, right? 1, 2, 3, 4, 5. I've got 5 cores running, right? This is a lot of waste. These processors are just waiting. These cores are just waiting. That's a lot of time wasted. They're just sitting there going like, well, you know. So really what people will do is they'll, the correct way, I would say, to do this is, so if I have 5 cores available, 1, 2, 3, 4, 5, I run this on a single core, so they just kind of like, you can think of it as serializing it, even though that's not how the processor is actually going to schedule everything, right? But you can think of it as just serializing it, basically putting them all in a line. But I'll just run 5 evolutionary algorithms at the same time. And then your computer should be smart enough to run 1 on each core, and then you're good to go, right? That's the way to do it. And I learned this because the people at Compute Canada got mad at me, being like, you're wasting so much time. And I was like, this is a great idea. They're like, no, this is a stupid idea. Just think about it. Oh, yeah. And then they showed me, just don't waste the time of the cores. Just hit run 5 times. Because usually, by the way, if you didn't know this, and we talk about this shortly in the class, whenever you want to analyze your algorithm, you can never hit run once and be like, here's my results. Who can tell me why? Come on, this should be obvious. Every run is so goddamn different, so you got to run it several times. You get a distribution of results, and then you generate some summary statistics and compare distributions of results. You can never compare a single run. You can't. Does anyone know this is trivia. So if you don't know, you're normal. Does anyone know the magic number that computer scientists love to use when doing comparisons? Like, how many times should I run something before I do any comparisons? I'll give you a hint. It's entirely arbitrary and bullshit. That doesn't help you? The correct answer that I should give you is you want your runs, you want to have a lot of runs. The more the merrier. The bigger your sample size is of the distribution of results you get, the more accurate any summary statistic you have. That's just the way it is. But the computer scientists always do like 30 runs, which is hilariously little. It just is. It's actually, whenever I do my stuff, I will never only do 30. Never. I do at least 100, which isn't even a very big number. But I do at least 100 runs. And then I get the results of the 100 runs, and then I do my comparisons after doing 100 runs. We'll talk about that, how to kind of go about doing that. Here. So soon. Any questions about that? So that's why the whole reason I brought that up was, I'm going to have to run my algorithm several times anyway, so just do it, like, just don't do this 5 times this way. Parallelize it by running the whole thing on one core and then just running the whole thing on separate cores. Honestly, I don't know why they're like 30. My guess is some asshole was like 30. So, okay.
I remember something related to statistics that if you have more than 30 samples, you can apply some assumption regarding the distribution of the samples.
So is it that it's actually 30, or is it that?
Yes,
Is it? Okay. Let's.
You can assume
You can assume normal distributions after 30? Oh, what the heck? 30. Here we go. So at the end of the day, it is still arbitrary. So a lot of the stuff in statistics is kind of arbitrary. But it looks like someone, somewhere, so this is where the computer scientists probably got it from. And I'll give you a little bit of a history lesson on science. Someone, somewhere, said 30. Because after 30, you have a reasonable expectation, assuming this is a direct quote. It looks like he's saying quote. It's a direct quote saying 30, you can get a reasonable expectation that you're going to have a normal distribution. Even though you should have even though we always assume normal distributions when that should never necessarily always be the case, but that's a whole other thing. Another thing in statistics, you know how it's always like something is significantly different, right? You've heard significantly different before, right? And what's the special threshold we use to make in order to say something is significantly different? Does anyone know? If it's, pardon? If the p-value is less than what? 0.05. They call that the alpha value of like 5%, 0.05. You want to know why it's 0.05? No one goddamn knows. Someone somewhere was like, 5%. And when we have a p-value, does anyone know what the p in p-value means? It means probability. It means the probability value. And what it means is, if you have two distributions, we are getting ahead of ourselves, but I think it's important to bring it up right now. If I have two distributions, if I'm observing something, if I'm observing the number of the clouds today, and I'm taking a measurement every 10 minutes, right? And I get a distribution, it'll look like this, right? Like at 10 o'clock, I saw that many clouds. At 11 o'clock, I saw that. At 11:30, I saw that. At 11:40, I saw that, and so on and so on and so on and so on and so on. I get a distribution that looks like this. And then I do the same thing a week from today. And I get a distribution like this, right? You can't really tell the difference. So the question I have is, like, hey, look, if I take the mean of today versus a week from now, there's a difference. On average, I saw more a week from today. Maybe I should be saying a week ago. Whatever, a week ago, but whatever. On one day, I saw more clouds than the other. Therefore, there were more clouds. And it's like, well, look at the distributions. Are those distributions actually different? You had a lot of observations, and you summarized a lot of information down to one statistic. And this is where you have to be careful. When people talk about statistics, statistics are summary values to describe more data. Okay? So the stats say, no, what does the data say? Entirely different. So, there's a difference. Now, this difference is something we could call the effect size, how different something is. The effect size is entirely different than if two distributions are, in fact, different. So what I want to do first is measure how different are these distributions. Distributions that look like this, right? I look at that and be like, yeah, those two things I was observing. This was thing one, this was thing two. They are, from the eyeball test, they're quite different, right? But let's do some actual statistics to tell me, okay, how different are they? When I'm looking at these two distributions, are they different? I don't know, maybe. So what I'll do is I'll do some calculation. Maybe I'll do a t-test, right? Really, you should do a permutation test. But a t-test is a quick and dirty way of getting something similar to what you would get with a permutation test. So a t-test, that was invented by a guy that worked at the Guinness Brewing Company, by the way, which is pretty interesting, will tell you how different two distributions are. And if the p-value you get is less than 0.05, let me put it this way, actually. Let me stop. Throw that alpha value out the window, the whole 0.05 out the window. When you get a p-value, whatever it is, that means there is a probability of, whatever the p-value is, that these two distributions are in fact from different things. Okay? So like that there is a significant difference between these things. No, there's no significance yet. P-value is just what's the probability that these two things are in fact different. No, I have this, and I flip it, flip it, flip it, flip it. It tells you that they are, okay, it depends on how you're looking at it. If I have a very small p-value, what is the probability that these two things are the same? That's what the p-value is telling you, actually. I had it backwards for some stupid reason. The p-value tells you how likely it is that these two observations came from the exact same thing. Okay? What is the probability that these distributions are in fact the same? So if you have a p-value of like 0.8, there's an 80% chance that there's no goddamn, it's the same goddamn thing, right? There's really no difference in the data. If you have a p-value that gets smaller and smaller and smaller and smaller and smaller, it's more and more likely that these things are actually different. But how far apart they are and how different they are not the same thing. Effect size is like, well, okay, are the distributions different? And like how different? They mean different things. We're going to go into more details on this in like a week. And it's important for you to know this. You should all know this. You've taken stats, right? Raise your hand if you've taken statistics. You don't know this? You should know this. I'm concerned. Not on you, but what happened? Anyways, effect size. That's like the measured, okay, what's the difference in the averages, for example? That's like an effect size, a cheesy way to measure the effect. But your distributions could be different. So if I have a very small p-value, that means the distributions are likely to be different. Someone somewhere said 0.05, that's the threshold to say something is significantly different. That's when we're happy, right? And science is obsessed with things being significantly different. But why 5%? Because really what you're saying is that there's a 5% chance that these things are the same. Really, that's what you're saying. Or something, if 5% is your threshold, right? If you go look, if you're doing a comparison of something and your p-value comes in at 0.05 exactly, there's a 5% chance these things are the same. It's significant. Therefore, I'm happy. But that means there's a 1 in 20 chance that they're not different, right? That's what that would mean, right? 1 time out of 20, your significant difference is entirely bullshit. It's not. Not to mention scientists cheese this all the time too. If you look at the plot of p-values in all science papers, here's 0.05, here's higher, no, here's lower, here's higher, let's say. You'll see like lower. There's a weirdly high number of values, in all like the scientific literature, there's a weirdly high number of values, just less than 0.05. Because if it wasn't less than 0.05, their work probably wouldn't be published. Meaning, what the hell is going on? Meaning, we know that there's a lot of bullshit out there, which is funny. So, anyways, yeah? Were you going to say something? Oh, okay. So the computer scientists love 30, but I don't. They've taken that to heart. So what happened was, you go back to the earlier days of machine learning, which isn't even that long ago, people were getting some results and saying like, oh, my results are good. And that was like the whole culture of the field. Until finally, somebody who knew a little bit about statistics showed up and said, what the hell are you all? This is entirely bullshit. You have to do more statistics. And my guess is some computer scientist who probably wasn't very good at math was like, well, how much do I need to do? And the statistician was like, at least 30. And then everyone in the room was like, 30 it is! And that's probably what happened. And this happens to so many scientific fields, is it starts to take off, and they are really bad with their analysis and statistics. They don't know what the hell they're doing. Because they never had to take, it was some arbitrary science, they were never really formally trained in statistics. And then eventually the field gets big enough where the statisticians show up and be like, you are all lying to everybody. All of your results are entire nonsense. This happens all the time. Happened in neuroscience not that long ago too. There was a famous, it wasn't a paper, it was like a poster presentation. Dead fish fMRI. The dead salmon study. Yeah, here we go. They threw a dead salmon using the statistics. Oh, come on. Do they not have the picture? They don't have the picture. Come on. Yeah. They put a dead fish, a dead salmon, in an fMRI and did all the statistics that the neuroscientists like to do. Where's the pictures? Why can't I get the pictures? My God. The internet is terrible now. Anyways. And they did all the statistics that you're supposed to do if you're a neuroscientist. Sorry, that all the other neuroscientists, not what they were supposed to do, but what they were all doing. And we're like, look, it's thinking. Which is, of course, nonsense. It's dead. But they were doing all the things that they did, which is standard operating procedure for the neuroscientists. And they concluded, like, hey, it's dead. This was a little while ago, and since then, neuroscience got kind of destroyed into doing things more correctly, which is a good thing, obviously. But like this happens to like every field. A new field kind of pops up. Like neuroscience wasn't a thing 50 years ago. I mean, not in the way it is today. And then, it gets bigger and bigger and bigger and bigger and bigger, and then they get a reality check that they're playing fantasy land and they need to do actual science. So, in other words, all science is bullshit. No one knows what they're doing. Back to evolution and computation. Here's another one, ring species. So talk about the island model. Ring species is another simple way to implicitly create a little bit of diversity in your population. What you do is you treat your population. So here's an example population of 24 chromosomes. Okay? They're all numbered 1 through 24. Okay? So this is a population. Envision in this spot there is a chromosome. Whatever it is, I don't care. When you do selection, you're only allowed to mate with individuals that are within some distance of you. So this guy can never mate with this guy. You create this like ring, they call this like ring species. And this happens in nature where they'll find like lizards that live around a mountain, and those that are on like opposite ends of that mountain can't mate with one another. They can't produce offspring. And because they're diverse enough and different enough. But they are like kind of the same species. It's interesting. So like ring species. So this is another way that people will add, like a mechanism to add diversity to the population. So further, there are no rules on how diversity should be measured. Should you do it in the genotype space? How similar are the chromosomes? Well, this depends on the encoding. Maybe you should use Hamming distance, Levenshtein distance, whatever you want. Phenotype space. How different are they in the phenotype space? What the chromosomes represent. This may be very different than the genotype space, depending on how direct or indirect your encoding is. So I don't know. Algorithm space. Some distance based on the algorithm's framework. For example, ring species and island model. But anyways. Any questions on that before we would start on Tuesday talking about genetic programming? We all happy? Sad? No? Awesome. Fantastic. All right, I'll see y'all later. Have a wonderful weekend.